Hello, physics students. This is Mr. Pham, and today's date is April 1st. April 1st, 2020. This is day 3 of our physics lessons, and I'm going to start off with what I left off with yesterday's video, which was I had this animation where these two massive objects are really, really close together, and I tasked you with trying to figure out what would happen to the force between these two objects if we decrease the mass to 5 billion kilograms apiece. So let's see what happens if I just reduce the mass of one of these objects to 5 billion kilograms. What do you think is going to happen to the force between these objects? Remember, Newton's law says that every object, every force is met with an equal but opposite force. So let's see what happens to mass 1 if we reduce it to 5 billion kilograms. All right, so we see that on mass 1, mass 2 exerts a force of 533.9 newtons. On the other hand, mass 2 has a force exerted on it by mass 1 of also 533.9 newtons. So what you see is that we decrease the mass of one object, we decrease the force between them, but they exert an equal but opposite force on each other. And there you go. You see that the force between them has decreased. Well, what do you think is going to happen? Let's see what happened to the force. We went from 10 billion kilograms to 5 billion kilograms. Look at the current force on this object. It's roughly 1,000. Well, by how much did the force decrease between them? Well, it went down roughly 2 times. It is now 1/2 the force that it was before. Well, what do you think is going to happen then if I reduce the mass of mass 2? Well, obviously, the force between them is going to decrease. Oop, a little too far. And it's now 267 newtons. So let's kick that back up to 10. We're at 533. By how much does the force get reduced because we reduced the mass by half? Well, we reduce the force between them by half as well. So that's what happens when you reduce the mass of objects. The force between them, if you keep them at the same distance, the force between them decreases. Okay, well, let's kick this back up. Let's leave it here. Let's leave it at 5 billion kilograms per object. What do you think is going to happen to the force between these two objects when I move them at a farther distance? Let's start off with 5 kilometers. Let's see what happens. Currently, I have a force of 267 newtons, which once again, it's not a lot of force between two massive objects. Of course, these things are really far apart to begin with, 2.5 kilometers. Let's see what happens. I love that sound. And 5 kilometers. 66.7 newtons is the current force. Now, if I go back, I see that the force is 267 newtons. But I go here to 5. I doubled the distance between them. What happened to the force? By how much did it go down by? Well, it went down roughly 4 times. It is 1/4 its original force. So when I had the two objects together and I decreased their mass, well, if I decrease the mass of one to half its mass, then the force went down by half. But when I increase that distance, the force between them goes down more. It goes down faster. So why is that? Is there a relationship then between force, distance, and mass? Well, there absolutely is. So let me kick it over to this screen here. So Newton, he's the guy that figured out everything about gravity. And he knew that the more massive an object, the more gravity it had. So let's take a look at these three masses of these common objects in our solar system. They're good reference points for our solar system because it's the planet we live on, the largest planet, and then the largest thing in our solar system. So if you look at the mass of Earth, it is 5.972 times 10 to the 24th kilograms. But you take that out of scientific notation, that's 5.972 billion million kilograms. I think I'm saying that right. It's a whole bunch of kilograms. So the Earth is massive. Then you compare that to the mass of Jupiter, and it is now, it's small compared. It's times 10 to 27. So Jupiter, obviously more massive. But then you compare that to the mass of the Sun. Well, it's got so much more mass than everything else. Obviously, it is the most massive object. So based upon those masses, which one of those do you think has the biggest gravitational field? Well, based upon the previous videos that I've released, it's the sun, obviously, is the most massive object. So gravity happens anywhere. Gravity is universal. Regardless of where you're at, anything with mass has gravity. And anything that has mass has a gravitational field, and it creates that ripple or that distortion in space-time. Well, we can represent this idea of gravity and mass and distance with Newton's law of gravitation. It is an equation that's going to allow us to calculate the force between two objects that have mass. We can do it at small scales. We can do it at extremely large scales as long as we know distance and mass. And this is Newton's law of gravitation. Now, I'm not going to work it today. I am, however, going to describe each part. So remember that force is equal to mass times acceleration. And that's kind of what you have here. You got distances, you got g, which I'll talk about in a second, and then you have masses, mass 1 and mass 2. And this is going to allow us to calculate that force between two objects. And they're going to be fairly massive objects. Now, this equation actually is very similar to something else that we're going to cover in a future video, something called Coulomb's law. And if you're one of my chemistry students, we've already had Coulomb's law. And in fact, this is identical to that, except for one number. So what we're going to do is we're going to calculate the gravitational force between two objects. So here's what each part means. F-grav obviously is the force of gravity between two objects. We're not going to look at three objects. Three objects, a little more complicated. There's a little interplay between the different parts. No, no, no. We can only do Newton's law of gravitation with two objects whose mass we know, or if we know another part. So G is an interesting thing. It's a universal gravitation constant. In science, you're going to find a lot of different values that represent something that's known, and it never changes. We call them constants. So for example, you physics students, you should know the speed of light by now in a vacuum. It's 3.0 times 10 to the 8 meters per second. That is the theoretical upper limit, how fast anything can travel, because light is the only thing that travels that fast. Nothing can travel faster than light. Well, to use Newton's law of gravitation, we had to have a constant, because if not, then things don't make sense. And we know that the constant, which is G, is 6.67 times 10 to the minus 11 newtons times meters squared divided by kilograms squared. Now, in chemistry, we've covered units like this and their purpose. I think we've covered this before. All right, I'm about to sneeze. Hold on. Nope, I don't think I'm going to sneeze. Oh, whew, it's close. But the whole point of this super complicated unit is to help us cancel out other things in the equation. That way we wind up with the unit that we're looking for. Really, I'm going to sneeze. Nope, not today. All right, so anyway, M1 is the mass of object 1. It's going to be in kilograms because, as you can see in the constant, it's kilograms. Mass of object 2. And then D is the distance separating the object's centers. Now, the thing about using this, and this is going to apply to Coulomb's law later, is that, you know, objects like planets, you have Earth and you have our atmosphere, uh, but where should you measure two super large objects in space that are really far apart? Well, some people might say, okay, well, you do it you measure them based upon the outer edge of these things, but really, Earth doesn't have an outer edge because it's an atmosphere that's full of gases. Same thing with the sun. The sun has a core and it's got a whole bunch of hot plasma or ionized gas surrounding it. And so the correct distance that we're going to use is always going to be from the center of the Earth or to the center of the sun. So if I'm measuring two objects, I go not from the outer edge of each of those, it's going to be from the exact center of those two large bodies. It's going to be for any two large bodies. So we are going to use Newton's law of gravitation to calculate any quantity. Now, G is always going to be the same, but it's the force, the distance, the masses that we're going to try and find. I'll provide you with one of these things or three of these things, and you'll always know G, and then it will be your responsibility to find the third thing. But you can probably kind of see what's going to happen when we use Newton's law of gravitation, because you've already seen this in the animation. If I have two objects here with a certain distance between them, they're going to produce a certain force. Well, what happened when I kept the objects the same distance from each other, but I reduced the mass of one of those objects? Well, the force went down, didn't it? And so we know then that if I increase something, it's probably going to increase something else, but not when it comes to distance. If I increase masses, I'm probably going to increase the force between two objects. If I decrease the masses, I'm going to decrease the force between two objects. But the distance is different. Because the distance is on bottom, because it's the denominator, numerator, denominator, yeah, it's the denominator, and it's going to divide into the other things, then something's going to happen to my force. When we increase distances, I'm going to decrease force. And so there's a relationship that happens then. And that means if I increase mass, that's going to equal an increase in the force of gravity, F grav. But if I increase distance between two objects, it is going to not equal an increase in gravity, is actually going to be a decrease in gravity, the force of gravity. And that is Newton's law of gravitation. So tomorrow I'm going to start working some problems, and then that will be your assignment. But today's assignment, yeah, I'm going to do that for every time I film all these videos on the same day. Today's assignment is I want you to describe identify two things that you learned in this video and describe them. Identify two things you learned in this video and describe them. And it's going to be on the same sheet as all of the other assignments that I've given you. So that's it for today. Hope you enjoyed it. Remember, if you have any questions, contact me on the various social media platforms and ways that I've described. But until then, I will see you tomorrow.